Okay, so we'll continue looking at expectations and variance. So we have a definition for both of them. Okay, but we will try to understand. We have some idea of what expectation does. Okay, it's a number that gives us some. It tells us something about the random variable, but we also know it doesn't tell us everything. Okay, now the variance is something like that. It's more a second order description of the random variable. So it tells us something more than just the expectation would tell us. But still, it's not the full story. Both the expectation and the variance together are also not the full story. Okay, so uh, let's begin by just recapping. So what is suppose you have a random variable x. And remember, we are only doing discrete valued random variables so far. Okay. So suppose x is a random variable. So what is the expectation of x? So can anyone help me with this? We had two different ways of saying it. Neither is optional. Both of them are important. So, but whichever you want to go first. So how do we define the expectation of x?
So the expectation of x would be the number of the population times the probability of x, right?
Okay, so tell me what I should write. So the number expectation of x would be. So let's write it formally. So x is a random variable. It
Oh,
takes
sure.
the
Suppose x is a random variable taking on values from set.
that's
Uh, I actually don't know. I'm sorry.
yeah. You can just call it x again. Like yeah. So the values right summation probability of okay. So that is one. So okay. So uh, Sam has one definition. So basically, we look at all okay, we look. So suppose x is defined over a universe omega. Okay, so expectation of x is I take every little outcome in the universe, write the probability of that outcome, multiply it by the number that x maps that outcome to. Okay, um, right, and sum over all of them. Okay, so what's the other way to define I mean the equivalent way to write expectations, right? So we're going to group together um, all the events where x takes on a particular value from a set. Okay, so this is the summation over every value the random variable can take. The probability x equals x. Okay, so uh, this is just a rearrangement of the first sum. Okay, the way I get the second sum is I group together right? And for every outcome in the event x equals x, x of omega is x of omega is little x, okay? And summing over all possible values is the partitioning of the universe. And so basically, like the this particular summation, it's not anything new. All we are doing is just rearranging the orders of rearranging the way we do the first sum. Okay, we just collect together all the outcomes, okay, such that the random variable maps the outcome to a value little x. Okay, when you collect all the outcomes on which the random variable takes the value little x, so that is the event the random variable equals little x. Okay, now on all of those outcomes, x of omega equals little x, so this summation is just a way of rewriting the first summation. Okay, now both of them are useful. There's some things that you can easily see from the first way of seeing things, and some things you can easily see from the second way of seeing things. Okay, so tell me, we also looked at some of the consequences. So suppose x is a Bernoulli p variable. Tell me, how do I compute the expectation of x? Okay, so if x is a Bernoulli p variable, then x can take on values what? What are the values the random variable can take if x is a Bernoulli p random variable?
1 or 0.
Okay, yeah, 0 and 1. Okay, so what is the expectation of x here? Right. So tell me in more detail. So since x can take on values 0 and 1, at 0 times the probability x equals 0 plus 1 times the probability x equals 1. And so this is the probability x equals 1, which is little p. Okay, it's a Bernoulli p random variable, right? So the p here refers to the probability x takes on value 1. Okay, so is everyone okay with this? Okay, now if x1 is a Bernoulli p random variable and x2 is a Bernoulli q random variable, and I don't tell you anything more about these random variables, I don't tell you the dependence. Okay, so what is the expectation of x1 plus x2? Right, at this point I haven't given you the probabilities of outcomes in the universe. Okay, because I didn't tell you how x1 and x2 depend on each other. Okay, just that individually they are a Bernoulli p and a Bernoulli q random variable. So we couldn't write, for example, what we don't know what's the probability x1 equals 0 and x2 equals 0. So those events we don't know how to write probabilities. Okay, but we can still compute the expectation of x1 plus x2. How?
Isn't it a linear operator? So we can look at expectation of x1 plus expectation of x2, like we can separate them.
That's right. So that's very good. So, but we'll do it step by step. So we use the first definition. It's the summation of all points in the universe, all outcomes in the universe, And this is how we get the linearity. Okay. X1 of, let me write it in color. Right. So we know arithmetic sums are they are commutative, they are distributive, so we use those properties. Right? So we are just using the distributive property first and then the commutative property. Okay, so together so this is just the expectation of x1, right? And this term is just the expectation of x2. This is why expectation is linear. Okay, so tell me, what is this? So expectation of x1 plus x2 here will be the sum of expectations of x1 and x2, which are very good. Right, so very good. Let me ask you something new. A is a number. A is some number. Okay. What is the expectation of A times X? Okay, X is X is a random variable and A is some number. Okay, so we want the expectation of A times X, hopefully in terms of the expectation of X. Okay, how do we do this? So this is something new. We haven't done this before, but can you tell me how to do this?
A is a random constant, right?
It's not a random constant. Like A is just a number. A is just some number. Okay, it's a fixed number. Like think of A as 2. Okay, A is a fixed number and X is a random variable. Okay, A is some fixed number. Like think A equals 2.
So can't we write the sum? Yeah, or we can just pull A out of the
Right.
sum.
So if you write it as the sum, very good. Okay, so here A times X is a random variable that assigns to every outcome of the universe a value equal to A times X of omega. Okay, so it's right. So this is what the random variable A times X would mean. Okay, and so here, like we have A is just a fixed number, so you can pull it out of this sum. So what you have is A times expectation of X. Okay, so that would be right. So when you scale a random variable by a constant, okay, you scale the expectation by the same constant. Okay, so everyone okay with this? Okay, so the first two examples we did, we have already done it before. So I was just using it so that you would sort of get into the class this one, but this is new. Okay, we haven't done this before. Right, so let's do a different thing. Let's say x1 and x2 are random variables. and they are independent. Okay, so x1 and x2 are two random variables that are independent. Okay, what is the expectation of x1 times x2? Okay, again, hopefully in terms of the expectation of x1 and expectation of x2. How do we do this? Okay, so if it helps, let's imagine that x1 takes values from the set script x1 or bold x1, and x2 takes values in this set. Okay, so x1 takes values in this set capital X1, and x2 takes values in this set x2. Okay, so what would be what can we do about the expectation of the product of x1 and x2? So expectation is a linear operator. So linear sums, linear combinations, we know what to do. Okay, but this is different. This is a product. Okay, so what would be the expectation of the product? How would we do it?
Is it gonna possibly be like two sums multiplied to
Like,
each other?
tell me step by step. Like, I'm not looking for the final answer, right? Like, so tell me like anything that gets me one step forward, but in a correct way.
All right. Well, my first thought is that because x1 and x2 have different values, or like their sets can be different. So like that to me means already that there has to be two sums, because you know if you sum over all the values in x1, you might not have covered all the values in x2,
Okay,
or vice versa.
so right, so let us. So in all of this, right, it is helpful to do it axiomatically. There is only one way we know how to define an expectation of a random variable. Okay, now here the random variable is the product of two random variables. Okay, so what it means is that we look at all points in the universe, so we write the probability of the outcome. Now this random variable x1 times x2, it assigns to every outcome the product of the values x1 and x2 would have assigned. Okay, so we would write x1 times omega, x2 times omega. Okay, now independence is a way, independence has to do with the way that the events x1, all the omega such that x1 of omega is little x1, the event all the omega such that x2 of omega equals little x2. Independence has to do with how these events intersect. Okay, it's not an outcome by outcome event. I mean, it's not something that you can determine outcome by outcome. Okay, it's something that is connected with how these events, or rather, how the intersection of these events are connected. Okay, so let's move on to the other definition. If x1 takes on values in the set capital X1, x2 takes on values in the set capital X2, the product, okay, takes on values where x1 can be any element of. Let me just move it to the next page so I can write this. I'm not changing anything. I'm just writing it in the next page so I have more space. Okay, now So this part is correct. Okay, this is the probability of all outcomes in the universe, and what the random variable x1 x2 does is to assign to every outcome the value x1 times omega times x2 times omega. Okay, so that's literally what it does. So completely okay so far. Okay, but it's not very useful because independence has to do with how these events intersect rather than something that we know from outcome to outcome. Okay, it's like we need to see these sets and how they intersect, not individual elements of the universe. Okay, so let's move on to the description that takes events together. Okay, now what we do is we group together all values x1 and take all values x2 can take. Okay, and we write probability x1 is little x1. Okay. No, let me write it this way. Okay, so this is the way I group this sum. Okay, so first I take every combination of values that the two random variables can take. Okay, now for each of those combinations, okay, so this sum means like first I group together into every combination of values of each of the the two random variables can take. Okay, so if for example x1 and x2 were Bernoulli random variables, okay, then all combination of values would have been 0 0 0 1 1 0 and 1 1. These are four different combinations of values. Okay, and so what I can do is to write them. So I look at every single combination of values and I group this summation based on these combinations of values. So everyone understands what I'm doing. Okay, so for the first combination of values, okay, I look at every possible outcome, okay, that belongs to the first combination of values. Okay, and here I look at the probability of that outcome. Okay, and here I multiply x1 x1 of the outcome times x2 of the outcome, but x1 of the outcome is all I know what it is. It is little x1. Let me write it in little more detail. I know what x1 maps this outcome to. Okay, so that is little x1. I know what x2 maps this outcome to. That is little x2. Okay, so when I do this, I get right, and I get the probability of all outcomes such that capital X1 equals little x1 and capital X2 is little x2. That we know is just the event. Right? So this part we haven't used independence. Okay, this is universally true. Okay, all this is universally true. It's always true. Like when you have probability expectation of x1 and x2. So here the complication here is that it's not something that depends on just one random variable. We're thinking of a random variable z that is related to two random variables. So that's the little bit of a hiccup. Okay, so this calculation will always be true, and we're going to do more examples. So if you don't catch this now, I'll know when we do the other examples. Okay, but is everyone okay with these steps? Okay, okay, so at this point, okay, from this point we are going to use independence. Okay, what does independence tell us? Okay, how can we simplify this sum? If we didn't know they were independent, this is all we can go. We can't do anything more than this. Okay, but if we know they are independent, there's something we can do to simplify this sum. How can you say, what is the joint probability of x1 equals little x1 and x2 equals little x2 if x1 and x2 are independent? Right, so we are moving from joint to conditional. Right, so you have events A and B. Okay, event A is the event random variable takes on value little x1, and event B is the event that random variable x2 takes on values little x2. Okay, so what's the joint probability of A and B? Actually, let's maybe do one more step. I haven't completed writing this. I'm waiting for something here. Right, so we want to move between joint and conditional probabilities like we always do. Okay, very good. So this is the probability. Excellent. Okay, so this is perfect. Now this one is also universally true, but when they are independent, we can make one additional simplification. What is that? When x2 and x1 are x1 and x2 are independent, we can make an additional simplification. What is that? Very good. Right, so the conditional probability, the conditional probability of x2 given x1 is just the marginal probability of x2. Okay, now at this point, you can use the properties of the commutative and distributive properties. Okay, here, for example, like we can break this sum like this. x1, I collect together all the, and maybe I write it. Okay, so I'm rearranging the four terms in the product like this. Okay, as far as so look at what is happening. So here these two terms only depend on x2, they don't depend on x1. Okay, if you're thinking of x2 as your variable in the summation, okay, as far as x2 is concerned, x1 is just a constant. Okay, so what I can do is, like, the summation that contains just the x2, I can move it inside. Okay, in effect, this is like rearranging the, this is like using the this is like rearranging the order of the sums and using the distributive law. Okay, and what I can then do is to treat this entire sum, right, so as a constant as far as x2 is concerned. Right, so this is again an application of the distributive law. Okay, now the first term is simply expectation of x1. The next one is simply the expectation of x2. Okay, so this is one of the things where two things are important when in deriving all of this. Getting to here is very important. The ability to start from something like this and get to something like this is very important. Also important is the ability to go from here to the fact that it's the product of the two expectations. Okay, and so this sort of rearrangement of the sums and so on. So I'm doing it not as so I'm doing this like okay. So I just this once. Okay, we'll do this in a more brute force way, just to see like where all these summations, where all these equalities with this manipulation of sums are coming. Okay, but in the future, like this should be something that comes automatically. It's not a probability concept, it's just something very useful everywhere. Okay, so here like this summation, for example, it is something like this: a1 a2 plus, or like a1 b1 plus a1 b2 plus a2 b1 plus a2 b2. So this is, imagine this sum looks something like this. Okay, now when moving from here to here, what we did was something like this. So we said a1 times b1 plus or rather like we said, when moving from here to here with this equality, okay, what we did was something like this: a1 times b1 plus b2 plus a2 times b1 plus b2. Okay, and when we moved over here, we said, okay, we are going to take b1 plus b2 times a1 plus a2. Right, so this is kind of how we manipulated these sums. Okay, now so this is probably something most of you are familiar with. Like you all know, like with summations, you can rearrange the sum in any way you want. You can use the distributive law, right? So and we have, this is just like rearranging the sum and using the distributive law 2 times. Okay, so that's all we have done, right? So, but in terms of summations, the way you think about it is that as far as this, if you treat x2 as this variable, as far as x2 is concerned, x1 is just like a constant. Okay, so these terms do not need to be inside the summation where we do where we sum over x2. Okay, so we can move that summation corresponding to just the x2 inside. Okay, now you notice that the first part only depends on x1, second part only depends on x2, so they can separate out as a product. Okay, so this is it's like a it's exactly what we have been doing with this, right? So here we collect, as far as b is concerned, a1, when we are looking at b1 plus b2, a1 multiplies both, so a1 is just a constant, we take it out. Okay, the second step, you just group together all the different terms corresponding to a1. Okay, so that is exactly the sequence of steps that is happening here. Okay, so this is like a more arithmetic thing. We won't spend too much time on that, but it is something you need to be comfortable with. Okay, but conceptually, what is happening is here. The ability to go from here to here is really important. Okay, and from here, like simple manipulation and the use of independence means that the expectation of x1 and x2 is the product of the expectations. Okay, and so this result is actually very important. If x1 and x2 are independent, then expectation of x1 x2 is the expectation of x1 times the expectation of x2. Right, so this is actually very important. It is also important to know that the converse does not hold. Okay, okay, so if you find So that means if expectation of x1, x2 is the product of their expectations, okay, it does not imply that x1 and x2 are independent. Okay, so it's very simple to see why this should be the case. Okay, so let's look at two random variables like this. So let's look at okay, let me give you okay, so we'll before I do that, like, is this completely clear? Okay, so everyone completely okay with this? Okay, so in order to show that, okay, so let us let's look at this. So the way we will show that the converse does not hold is to simply give a counter example. Okay, so but let's also do one more thing just to verify that this part is completely clear. Tell me what is, suppose I look at expectation of x1 squared x2. Okay, so tell me how you would simplify this x1 expectation of x1 squared times x2. Okay, so we've simplified x1 times x2, right? So tell me how I would work with the expectation of x1 squared times x2. Right? So tell me how to simplify. Just like we did for expectation of x1 times x2, right? How would I go about trying to simplify expectation of x1 squared x2? So basically it is something like this, right? So we started off, sorry, right? We started off from here and moved till here, right? So that's what we want to do. Okay. But tell me how I would try to simplify something like this: the expectation of x1 squared times x2.
I think I would start with a sum
Okay.
over both x1 and x2,
Okay.
and then I would have x1
So this is the
squared.
sum of all the values that x1 and x2 can take respectively. Okay.
Mhm.
Right.
And then I would have x1 squared times x2 times the probability of x1 intersection x2.
Right.
Oh yeah, yeah, like that.
Very good. So is everyone completely okay with this? Okay. What about something like this? Expectation of 2 to the, how would we do this? Let's do e to the this one because we are going to do this anyway. Okay. Expectation of little e to the x1 plus x2.
Um, again, I would sum over the all values that x1 and x2 can take.
Right.
And then, but this time you'd have e to the x1 plus x2, and then the probability of x1 equals little x1 intersect x2 equals little x2.
Right. So very good. So is everyone right? So Axel is the only one answering, but are others okay with this? Okay. Okay. So if x1 and x2 are independent, okay, can you simplify e to the x1 and e to the x1 plus x2 for me? Right. So we have summation over x1, summation over x2. Okay, all values the random variable x1 can take, x2 can take, e to the little x1. So actually, let me write. So hopefully my letters are this one. So these are capital letters. Okay, and here these are small letters. So e to the x1 plus x2. Okay, what is e to the x1 plus x2? Right. So if x1 and x2 are independent, how can we simplify this further?
With the next thing that you write is e to the x1 probability of x1 equals little x1.
Very good. Right. Continue.
And then multiply that by the summation, or wait, maybe I'm jumping ahead.
No, that's okay. Yeah. Continue.
Okay. The summation of the same for x2 now, exponent x2 times the probability of big x2 equals little x2. Yep.
So this is the expectation of e to the capital X1 times the expectation. Okay, so is everyone okay? Okay, this is actually a very, so this one, so in this course, we won't use too much of this. Okay? This is not a super crucial thing for this course, okay, but this is a very important observation in general. Okay, so when you do a little more advanced things, this sort of equality is very critical. Okay, one of the reasons is that when you try to bound the deviations of random variables around their expectations in ways more sophisticated than what we do in this class, you go through arguments that start like this. Okay, so in any case, okay, so this is good. So everyone knows how to write expectations of functions of random variables. Okay, so what you have here is like you have a bunch of different random variables and it's some arbitrary function of a bunch of random variables. Okay, so that's what you had here, here x1 times x2, x1 squared times x2, e to the x1 plus x2, e to the x1 times x2, like whatever it may be. Okay, when you write the expectation of functions of multiple random variables, so this is how you simplify it. Okay, good. So let's go back. So remember that if x1 and x2 are independent, then expectation of x1, x2 is the product of the expectations. We proved this and we said that the converse is not true. Right? And so here is an example. So I take x1 and x2. Let us say x1 takes on values, x1 can take on values 0 or 1. No, let's do it this way. Okay, so let's compute the expectation of so what sort of a random variable is x1? I mean, what values can x1 take? What are the values x1 can take?
So -1 and 1.
Right, so -1 and 1. x2 can take what values?
1, 2, -1, -2.
-2, -1, 1 and 2. What's the probability distribution of x1? Right, so what's the probability x1 can? It's -1.
So 1/6.
No. What's the probability x1 is negative?
Oh, I'm sorry.
1/2.
1/2. Yeah.
Right? And what's the probability x1 equals 1? Has to be the complement, right? So these two are complements of each other, so that's also 1/2. What's the expectation of x1? Right. So -1 times 1/2 plus +1 times 1/2, which is 0. Okay. What is the expectation of x1, x2? So what is x1, x2 here? Here it is 2. Here it is -1. Okay, here it is -1. And here it is 2. The product of x1 and x2, right? So what's the expectation of x1 and x2? The values x1, x2 can take. So 2 times 1/6, -1 times 1/3, -1 times 1/3, plus 2 times 1/6, which is 0. Okay, so expectation of x1, x2 is 0, and expectation of x1 is 0. So expectation of, so therefore we have expectation of x1, x2, which is 0. It has to be, we didn't compute the expectation of x2, but we don't need to, okay, because this is 0 and this is 0. So it really doesn't matter what expectation of x2 is, okay. Now, what is x2 are x1 and x2 independent? Okay, can you tell me without computing anything? Are they independent? So Quinn, why do you say yes? Okay, so one quick way to no. So it's precisely what we are saying. The fact that the expectation of x1, x2 equals the product of their individual expectation does not necessarily mean that they are independent. The converse here is not true. Okay, so right. So this is exactly what we want to show. Here we have a case where x1 and x2 satisfy expectation of the product is the product of their expectations, but they're not independent. And the quickest way to see that is that when x1 equals minus 1, the values x2 takes on are negative 2 and 1. Okay? When it is plus 1, it takes on a whole different set of values, minus 1 and 2. Okay? So in fact, if you see x2 equals plus 2, okay, you know x1 has to be plus 1. x1 cannot possibly be minus 1. Right? Do you see that? Right? So for different values of x1, x2 takes on a whole different set of values. Okay, so there's no way that the marginals can be is independent of the conditionals. Okay, so the marginal distribution of x2 given x1 is definitely not. The conditional distribution of x2 given x1 is definitely not the marginal of x2. Okay, so I'll let you think about this, but we are running out of time, so I'll stop. If you have questions, like, you can just ask me. Okay, so here x1 and x2 are not independent. Okay, so when they are independent, you can write the product expectation of their product very easily as product of their expectations. But when they're not but just because the expectation of the product is the product of the expectations, it does not tell you anything about their independence. Okay. Okay, so does that make sense? So does that make sense? Okay. Right. Just 1 second. So does that make sense? Okay. Okay. So we'll stop here and we'll continue next class. Okay. Yeah. I'll stop.